Okay, so now we're going to look at how sine graph or sinusoidal graph transforms when you make certain changes to the function. So first of all, we need to quickly recap on some of the terms that we know. So firstly, let's look at amplitude, and the amplitude is the distance from the midline of the graph to the peak of the graph or the trough of the graph. So we can see here that the amplitude of this sine wave is 1. Okay, so the amplitude is 1. Now, what is the midline? So we see that the midline is the x-axis here in this particular graph, but it's not always the x-axis. It's basically just any line that the sine wave is fluctuating around. So the wave is symmetrical around the midline, and it fluctuates into peaks and troughs either side of the midline. And I suppose the distance or the amplitude is equal on either side of the midline. And then we need to know how to find the period, and the period is just how many radians is in one full cycle of the wave. And we can see here that one full cycle of this wave takes us from, well, if we start our reference point here at the origin, we go through a peak and then down and into a trough, and then we're back to 2 pi here. So the period of this graph is 2 pi. So we see it there, it's 2 pi. Okay. So now let's look at what happens when you have a coefficient for your sine function. So on the left hand side of the page here we have a sine graph, okay, and it's the same as what we're used to. It starts here, the sine of 0 radians is 0, goes through a peak, goes through a trough, and we get back to 2 pi. And as we know, the range of a sine graph goes from +1 to -1. So let's highlight that here on the y-axis. So from +1 to -1 is the range of a sine wave, and it's also the range of a cos wave. And so let's make a note of that underneath. So the range of this function is from -1 to +1. Okay, so if I put in here, for example, if I look at the sine of pi over 2, so the sine of pi over 2 is 1. Well then, 2 times the sine of pi over 2 is going to be 2 times 1, which is 2. And I can see here on my graph on the right hand side that the range of this graph goes from 2 to -2. So we'll put that in. So the range of this graph is from -2 to +2. And so we can see then that the amplitude is going to change in both graphs. The amplitude of my sine x graph is 1, but the amplitude of my 2 times sine x graph is 2. So the consequence of multiplying my sine x by 2, I have a coefficient now of my sine x function. So 2 sine x means I have an amplitude of 2. So to generalize this, if I say f of x is equal to b times sine x, then b is my amplitude. It's the amplitude of the wave. Okay, so f of x is the function b sine x, where b is the amplitude of the wave. So in this example, I have sine x and then I have sine 2x. So now instead of having a coefficient for the entire function of sine x, I have a coefficient of the angle. So sine 2x means that where x is the angle, it's now multiplied by 2. So I have a coefficient for the angle in this case. Okay, so now let's look at sine x on the left-hand side. So it goes from 0 to 2 pi as usual. But if we look at sine of 2x on the right-hand side, we can see that there's sort of a compression happening here, where the wave seems to have been squished together. So it seems that the wave on the right-hand side has been compressed. So let's have a look at why that would happen. So first of all, let's look at sine x on the left-hand side. And I'm again going to look at the sine of pi over 2. And I can see that the sine of pi over 2 is 1. Now let's see what happens when I have an input of pi over 2 into sine of 2x. So let's write this out. So my input for my function is pi over 2. So let x equal pi over 2. And when I input pi over 2 into sine of x, I get sine of pi over 2 is equal to 1. I read that from my graph. What happens then when I fill in x into sine of 2x? So the sine of 2 times pi over 2 is the sine of pi. And again, from my sine graph, I can see what the sine of pi is. So let's highlight that. And the sine of pi is 0. So the sine of pi is 0. And that is why when I input pi over 2 into the sine of 2x graph, I get that sine of 2 times pi over 2 is 0. So I have a different output here, and the effect of that is to sort of compress my graph or to squeeze it in. So let's now have a look at what effect this has had on the period of the wave. So the period of the wave we can get by taking the origin here as our reference. We'll go through a peak, we'll go through a trough, until we get back to the same point in the cycle again and before it starts repeating itself. So pi then, if you can see that, I know it's kind of small on the screen, but that is pi radians. And pi radians then is the end of the cycle. And so I can see from 0 to pi is my period. My period is pi radians. So it's half of the period for the sine x graph. So if I was to generalize this, let's say I have the function f of x is equal to sine of c times theta. Well then the period of this function is equal to 2 pi divided by c, and it's the absolute value of c. Okay, so that would mean that in this case the sine of 2x, the coefficient is 2, so my period is equal to 2 pi divided by the absolute value of the coefficient, which is 2, and that gave me pi radians as my period. So on this slide here, we are looking at a sine x graph again on the left-hand side, so we have something to compare with. And on the right-hand side, this time we have sine of a half x. So the coefficient of x, our input, or the coefficient of the angle, is now a half of x. And so as we saw in the last video, if you want to find out what the period of this graph should be, we can say that the period will be 2 pi divided by the coefficient of the angle, which is a half. So it's divided by a half. And we know that when you divide by a fraction, that means you flip it or you turn it upside down, you get the reciprocal and you multiply by that. So I multiply by 2 over 1 and I find that my period of my graph should be 4 pi. And let's check and see if that is correct. So if I take again 0 as my reference point here and I go through a peak, I go down through a trough until I get back to the same place where I started, and I'll highlight that, and I can see now that instead of going through 2 pi radians, I've actually gone through 4 pi radians. So the period is 4 pi and my calculation is correct. Okay, that's the period. So here I have the two waves side by side, and we can compare the two. And I suppose one of the ways I like to think about this to get my head around what's happening is to think of the coefficient of the x input, this 2 here on the left and this half here on the right, as being analogous to the speed of the wave. So if I think about the left hand side and its sine of 2x, the 2 tells me that this wave is travelling twice as fast as a sine wave. So it's able to cover double the ground. So I can see that it gets through one full cycle after pi radians. Okay, so it only takes pi radians to get through one full cycle. And after 2 pi radians, it's actually after getting through 2 cycles. So a sine wave will get through one cycle in 2 pi radians, but this sine of 2x wave gets through 2 cycles in 2 pi radians. So it's travelling faster. Whereas on the right hand side here with sine of a half x, this should be going half as fast as an ordinary sine wave. So I can see that it actually takes 2 pi radians to only get halfway through the cycle here, and it needs another 2 pi radians to get all the way through one cycle. So this wave is going much slower and it's much more drawn out. Okay, and what I just want to quickly point out here is a common error that students make. They mix up the 2 here, which is the coefficient of the sine function, or the 2 here, which is the coefficient of the x input. So the 2 on the left hand side, as we can see, tells us that the amplitude of the wave is 2. So that's amplitude. Okay, so the amplitude here is 2, whereas the 2 on the right hand side tells us that the period has changed. So if your 2 is outside of the sine function, we're talking about amplitude. But if your 2 is inside the sine function, we're talking about the speed of the range, and that affects the period, or the how many radians it takes to get through one full cycle. So the period of this wave is 2 pi over 2, which is pi radians. Okay, so just be very careful that you take note that if the coefficient, or the new coefficient, is outside of the sine function, it's describing the amplitude. And if the coefficient, so this is the amplitude here, but if the coefficient is inside the function and it's the coefficient of x, well then it affects the period. So this coefficient here tends to stretch the wave in the vertical direction, stretch or compress it in the vertical direction, whereas this coefficient here tends to stretch or compress the wave in the horizontal direction. Okay, and the very last type of transformation that could happen would be if we were to add or subtract a constant to our function. So here on the left hand side I have the sine graph again, and it's just so we can use it for comparison. And on the right hand side then I have the sine graph, but I've added 1 to it. So I can see on the left hand side the midline of my graph is, as I've seen before, it is the x-axis, but it's basically the line around which my wave fluctuates, and the wave is symmetrical around that midline. On the right hand side I can see that my midline has now shifted up the y-axis, and it's going through y is 1. In fact, the equation of that line is y is equal to 1. And so adding the constant 1 to my function has had the effect of just shifting the function up the y-axis by 1. And if I was to draw the graph of sine x minus 1, I would, of course, get a pencil. We always do our graphs in pencil. And I would simply draw the graph so that the midline was shifted down the y-axis by 1. So my midline is at minus 1 now, using a pencil, sorry. So my midline is at -1. So that means that when I start my graph, it's on the midline. I will go up to the peak of my graph at pi/2, and I'm just mirroring the graph as above, but yet the midline of this graph is going to be through -1. At pi, I'll find myself back at the midline. For 3 pi/2, I'll be down at the trough of the graph, and then for 2 pi, I'll return to my starting point right there in the midline, and I draw my graph, and you always draw your graphs in pencil. And so that graph there is the function sine x -1. And so here I have exactly the same type of transformation, except I'm using the cos x graph. And the cos x graph is a sinusoidal graph. And no matter whether I change the coefficient of the function, so it changes the amplitude, or if I change the coefficient of the x input here, which will change the period, or if I change or if I add or subtract a constant from the end, the effect on a cos graph will be the very same as the effect on a sine graph. Okay, so by adding -2 to this cos function, it means the cos function is going to shift down the y-axis by -2, and I can highlight my midline here at -2, and I can see that the cos graph fluctuates around that midline. And so now what I want to do is take all of what I've learned about how changes to a trig function can change the graph of the trig function, and I want to put it all together into one function and try and draw this function. So in front of me here I have the general term for a trig function. It is f of x is b cos of c theta plus a, and let's go through each of these. So the coefficient of the function, so that is b here, the coefficient of the function. That describes the amplitude, okay? So b here is 2, so the amplitude of this function is 2, okay? The period of my function, so the period of this function is going to be given by 2 pi divided by c. Okay, so the coefficient of the input x here is 1/2. That means it's slower than an ordinary cos x graph, and I'm going to see that my wave is more stretched out. It's going to take me more radians to complete one full cycle. And so let's calculate what our period is. The period of this wave is 2 pi divided by 1/2, which is 2 pi over 1 multiplied by 2 over 1, so it's going to be 4 pi. Okay, 4 pi. I also know that my midline of my graph is going to be given by the constant at the end, and the constant at the end of this function is -2. So the midline of my graph is going to go through -2. Okay, down here. So let me draw that in now. One sec now. So the midline of my graph will go through this line, y is equal to -2. So I'll be starting my graph at 0 radians, and I know that when I have 0 radians, the cos of 0 is 1. So 2 times the cos of 0 will be 2. So I'll go from -2 up to 0. And so the start of my graph will be here at 0. I know that I'll complete one full cycle of my graph after 4 pi radians, so I'll pop that in there as well. So I'm starting my graph at the peak of its amplitude. That means I'll reach the trough of this graph, or of this wave, halfway between the two peaks. So I'll have a peak at 0, I'll have a peak at 4 pi, so I must have a trough halfway between them, and that will be down here at -4, and that'll happen when I have 2 pi radians. So I'll pop that in there as well. Okay, and I know that since my amplitude is 2, then my range must go from 0 to minus 2 and all the way down to minus 4. Okay, and then so halfway between my peak at 0 and my trough at minus 4, I must cross the midline, and so crossing the midline will happen at pi. And so I'll cross the midline again between 2 pi and 4 pi, so that will be at 3 pi. So I'm just trying to put in these reference points because I know the general shape of my cos graph, and I want to put in these reference points taking account of my amplitude and of my period of 4 pi. And so I'm going to draw in my graph now. And I'm going to go down through the midline into my trough, back across the midline and back into the peak of the cos graph. And so that is one full cycle of 2 times cos half x minus 2.